In 1895, a Russian scientist named Konstantin Tsiolkovsky visited Paris and stood beneath the Eiffel Tower. The tower, completed just 6 years earlier, was then the tallest man-made structure on Earth, 300 meters of wrought iron reaching into the Parisian sky. Standing at its base and looking up, Tsiolkovsky began to think about what it would mean to extend such a structure not to 300 meters, but to 36,000 kilometers, all the way to geostationary orbit. He published his speculation in 1895. It was treated as fantasy. More than a century later, the concept he sketched has been worked through in extraordinary engineering detail by physicists, material scientists, and aerospace engineers at institutions including NASA, the International Academy of Astronautics, and multiple universities. What they have found is not that the space elevator is impossible. They have found that it requires one specific material with one specific property, and that for most of the 20th century, that material did not exist. The story of the space elevator is, at its core, the story of that material. The physics of a space elevator are based on a phenomenon called geostationary orbit. At an altitude of approximately 35,786 kilometers above the Earth's equator, an orbiting object moves at exactly the speed required to remain stationary relative to a point on the ground below. Communication satellites are placed in this orbit deliberately. It allows a satellite dish to point at a fixed point in the sky without tracking. Now imagine attaching a cable to a satellite in geostationary orbit and letting it hang down to the surface. The satellite is moving at orbital velocity, which generates centrifugal force outward, away from the Earth. Gravity pulls the cable and satellite inward toward the Earth. At the geostationary altitude, these forces balance exactly. The cable hangs taut, held in tension between the gravitational pull on the lower portion and the centrifugal pull of the orbital mass at the upper end. A structure like this, a cable reaching from the ground to orbit and beyond, would allow objects to climb the cable from the surface to orbit without the expenditure of enormous amounts of propellant. Instead of the rocket equation, which demands exponentially increasing fuel mass for increasing payload, you have a mechanical system. A climber ascends the cable using electrical power. The electricity can be generated from solar panels on the cable itself or transmitted from the ground. The energy required to lift 1 kilogram of payload to low Earth orbit by rocket is currently in the range of several thousand kilowatt-hours of equivalent energy, when accounting for propellant costs. A space elevator operating at high efficiency would require a fraction of that, perhaps 50 to 100 kilowatt-hours per kilogram. The cost reduction would be transformative. Access to orbit would become cheap enough to radically alter the economics of satellite deployment, space manufacturing, and eventually human spaceflight. This is the promise. The obstacle is the cable. The cable of a space elevator must be simultaneously extraordinarily strong, extraordinarily light, and extraordinarily long. The engineering requirement is expressed as a ratio called specific strength, the ratio of a material's tensile strength to its density. The higher the specific strength, the better the material can support its own weight across the length of the cable while still carrying payload. The specific strength required for a space elevator cable, calculated from the physics of the system, is approximately 47 to 63 gigapascals per unit of density. Expressed in the units typically used for this calculation, approximately 76 gigapascal cubic meters per kilogram. Steel, the strongest structural material in common use, has a specific strength of approximately 0.4 gigapascal cubic meters per kilogram. It falls short of the requirement by roughly 2 orders of magnitude. A steel cable hanging from geostationary orbit would be crushed by its own weight long before it reached the ground. Kevlar, glass fiber, and other high-performance materials do better, but none of them come close to the required value. Carbon nanotubes, discovered in 1991 by Japanese physicist Sumio Iijima, are the material that changed the conversation. A carbon nanotube is a cylinder of carbon atoms arranged in a hexagonal lattice, rolled into a tube with a diameter measured in nanometers, millionths of a millimeter. The carbon-carbon bond is one of the strongest chemical bonds in nature. In a nanotube, this bond is expressed in a geometrically optimal configuration that distributes stress across the entire structure with extraordinary efficiency. Theoretical calculations of the specific strength of defect-free carbon nanotubes yield values in the range of 100 to 176 gigapascal cubic meters per kilogram. This is 2 to more than twice the value required for a space elevator cable. The material, in theory, is strong enough. The problem is that theory and manufacturing reality are separated by an enormous gap. Carbon nanotubes are synthesized in laboratory conditions, and individual tubes can be produced with properties close to the theoretical values. But the space elevator cable requires carbon nanotube fiber at length. A practical cable would need to be many tens of thousands of kilometers long. Manufacturing a continuous nanotube fiber of even a few centimeters with uniform, defect-free properties has proven extraordinarily difficult. Defects in the lattice, missing atoms, structural irregularities, points where tubes join imperfectly, reduce strength dramatically. The longest single carbon nanotube fibers produced, as of recent years, measure in the range of half a meter. The gap between half a meter and 36,000 kilometers is not merely quantitative. Additionally, carbon nanotubes face vulnerability to atomic oxygen in low Earth orbit. The highly reactive oxygen atoms present in the upper atmosphere at altitudes of around 200 to 800 kilometers degrade carbon materials over time. A cable passing through this region would require either protective coating or material substitution in the vulnerable altitude range. Researchers have proposed alternatives and complements: graphene ribbons, diamond nanothreads, and other carbon allotropes with potentially suitable properties. None has yet demonstrated the combination of strength, defect tolerance, and manufacturable length that the cable requires. The engineering design of a space elevator extends well beyond the cable itself. The anchor point at the base must be located on or near the equator. The physics of geostationary orbit require equatorial positioning. It must be able to withstand the enormous tension of the cable. Most serious proposals locate the anchor on a mobile ocean platform, which allows repositioning to avoid orbital debris and weather systems, and removes the political complication of choosing a specific equatorial nation as host. The counterweight at the upper end of the cable, above geostationary orbit, provides the centrifugal force that keeps the cable taut. It would need to be massive. Estimates range from tens of thousands to hundreds of thousands of metric tons, depending on cable design and payload capacity. One proposal uses a captured asteroid as the counterweight. Another uses the accumulated mass of construction materials sent up during the building phase. Climber vehicles, the machines that actually carry payload up and down the cable, present their own engineering challenges. They must grip the cable securely while moving at speeds that make the journey to orbit practical, perhaps several hundred kilometers per hour. They must be powered continuously, most likely by laser or microwave power beam from the ground or from stations along the cable. They must avoid colliding with each other on a cable that will ultimately be handling significant traffic. The threat from orbital debris is serious. The cable is a fixed structure in an environment where objects move at orbital velocities, 7 to 8 kilometers per second. A piece of debris impacting the cable at that velocity would carry enormous kinetic energy. Analysis suggests that a full-width cable would face statistically significant impact risk over time. Most serious designs address this with multiple parallel strands in a ribbon configuration, such that a debris strike severs some strands, but not all, with the remaining strands carrying the load while repairs are made by robotic systems climbing the cable. The economic and civilizational implications of a working space elevator are worth stating directly, because they're transformative in a way that incremental improvements to rocket technology are not. Rocket launches currently cost, depending on vehicle and configuration, somewhere between $1,500 and $10,000 per kilogram delivered to low Earth orbit. Reusable rockets have brought these costs down dramatically from historical levels, but the rocket equation imposes a fundamental floor. A significant fraction of the vehicle's mass must always be propellant, and propellant has cost and mass that cannot be wished away. A space elevator, operating at the energy efficiencies its physics allow, could potentially reduce the cost of reaching orbit to tens of dollars per kilogram. At those costs, the economics of space manufacturing, space-based solar power, and human presence beyond Earth change completely. Materials that are energetically cheap to process in zero gravity or vacuum, but currently prohibitively expensive to deliver, become commercially viable. Space-based solar power stations, which can collect sunlight continuously without atmospheric absorption and beam it to Earth, become competitive with terrestrial energy sources. The space elevator is not merely a transportation technology. It is an economic threshold. Cross it, and the relationship between Earth and the rest of the solar system becomes fundamentally different. The cable is the problem. The cable remains unsolved. But the physics are sound, the engineering pathway is understood, and the material science is advancing. Whether in 50 years or 200, the question of the space elevator is not whether it is conceivable. It is whether we develop the materials, science, and manufacturing capability to build the cable before something else gets us to orbit cheaply enough that the need is less urgent. Both problems are worth solving. Only one of them breaks the rocket equation entirely.